So in Chapter 2, we're going to start off by examining how we simplify expressions involving powers and the rules of exponents. And also we're going to be using scientific notation. So part of your vocabulary here would be scientific notation. Remember, scientific notation involves one decimal place to the left of the decimal, and then however many you need, for instance, 1.03 times a power of 10, let's say 10 to the third power. This would represent the number, if I move this decimal place 3 places, 1, 2, 3 would create a 0, 1, 0, 3, 0. So 1030 could also be written as 1.03 times 10 to the third power, which you should already be pretty much aware of. One thing that we would use scientific notation for, if you study astronomy, you'll use scientific notation a fair bit, partly because it helps you to calculate very large distances, and also the rules of exponents apply in that realm. So as we work on a problem like this, talking about Betelgeuse, which is one of the stars found in the constellation Orion, it's right up here at Orion's shoulder, has a radius that is 1,500 times the radius of the Sun. If we want to then make a comparison of the volume of Betelgeuse to the volume of our Sun, we can use the properties of exponents to go ahead and work with that. So we'll solve this problem a little later, but here's some background information for you. So when we look at the properties of exponents, and we're going to visit these again later in the semester, the product of powers property says that if I multiply two items that have the same base and have exponents, then I can just add the exponents. The power of a power says that if I have an item, a power, so that's a base being taken to an exponential power, if I take the power to a power, I multiply the exponents. If I have two numbers that are being multiplied together that are being taken to a power, or for instance, if I can take a value that is being taken to a power and factor it into two separate factors, then it would be each of the individual factors taken to the same power. I have the idea of negative exponents. So if I have a negative exponent, I can simply invert the power and make the exponent positive. So a to the negative m power becomes 1 over a to the m. Any number to any base to the 0 power is equal to 1 except for 0. And then these two properties are very similar to properties we had up above here. If I have, quotient of powers is similar to product of powers. If I have two items with the same base being taken to powers, I can subtract the powers when they're being divided. When they're being multiplied, I added the powers. When they're being divided, I subtract the powers. And power of a quotient is similar to power of a product. Again, if I can take this item that is two numbers being divided, being taken to a power, it's the first number, the numerator being taken to the power over the denominator being taken to the same power. And over here we have examples of how these play out. So take a minute and take a look at those. Go ahead and pause the video if you need to, so you can see how these things function. Okay, I'm going to go ahead and do a couple of examples. Actually, let me go back. I do want to talk about what's key here is you'll see that we're dealing with different things being in common. And what do? When I have the same base, then what I do is I work with the exponents. You'll notice the base did not change in any way. So when I was working with items with the same base, and that's here in the product and also in the quotient property, you'll notice that the base of the power did not change. What I did is I left the base alone, and instead I worked with the exponents. All right? Now, if you take a look at the product, power of a product or power of a quotient, you'll notice that the exponents stay the same. The exponents don't change. And instead at that point then I'm working with the bases. So what you will find is that there's no time when I'm working with both the bases and the exponents at the same time. Okay, so that's something really important to keep track of, is how these properties play out. Either I'm working with items with the same base, then I leave the base alone and I work with the exponents, or I'm working with items with the same exponents, and then I leave the exponent alone and I work with the base. Okay, so in practice here, I have two items with the same base. The base stays the same, and because I'm multiplying, I add the exponents, so this becomes 3 to the 5th power. Here I'm taking a power to a power. This becomes 2 to the 4 times 2 power, which is 2 to the 8th power. Okay, this item is going to be, it's going to be a little complicated because I have the negative 3 power, right? Which means that I'm going to be able to say, first I do the quotient property, and then what these do is they invert. So I'm going to show you every step that happens here. That becomes 1 over 2 to the 3rd power, and this becomes 1 over 7 to the 3rd power, and that's going to equal, right, 1 over 2 to the 3rd power times, right, when we divide by a fraction we invert and multiply, and that becomes 7 to the 3rd power over 2 to the 3rd power. So if you take a look compared to my initial problem, what I really did is I inverted the fraction and I made the power positive. So I showed you every little step that happens, but easily you could simply go from one to the other as long as you're clear about what it is you're doing, right? These other steps here in the middle, we're justifying this, but they're really not that necessary. Here I have items with the same base, so I have 3 to the 4th. I'm dividing, so I'm going to subtract the exponents. 4 minus negative 2 becomes 3 to the 6th power. If I wanted to do this problem another way, I could say, well, this is 3 to the 4th over 1 over 3 squared, and then of course if I divide by a fraction, I invert and multiply, so that'll be 3 to the 4th times 3 squared over 1, and now I'm multiplying and I'm adding the exponents, and I still get 3 to the 6th power. So you could have done this problem either way. Both are certainly correct. Okay, a few more complicated examples, right? Negative exponent, so this becomes 1 over. The base doesn't change, but the exponent becomes positive. That will be 1 over 3 to the 3rd power, right, which is 27. A cubed to the 3rd power, so I multiply the exponents, that's a to the 9th. B to the 5th to the 3rd power, again I multiply the exponents, that's b to the 15th. And there's my answer. Okay, over here we're going to work with simplifying some things. You'll notice that I've got coefficients, I've got a variable of c, and I've got a variable of d, and I'm going to deal with them individually. Right? 3 goes into 9 3 times, so that part simplifies to be 1/3. I'll have c to the 3rd and c to the 1st power, so that's c to the 3 minus 1, that's c squared. And I'll have d to the 1st minus negative 1, that's d squared. So this could be 1/3 c squared d squared. Or I could write it c squared d squared over 3. Either one of these is correct. Okay, so I want you to pause the video now, and I want you to do some practice work. This is related to what I've just gone ahead and showed you, so please do these particular problems from the homework. And when you're done, go ahead and start the video again. Now we're going to work a little bit with scientific notation. What's nice about scientific notation is it lets me take numbers that are very large and make them relatively small, And what I end up doing is I end up doing the notation by separating the base of the scientific notation from the power of 10 that's associated with it. So what I can do here is I can do 4.2 times 1.5, and that's going to be times 10 to the third times 10 to the sixth. So I know that this is all going to be times 10 to the ninth power. And now all I'm doing is I'm multiplying 4.2 times 1.5. And that's going to equal 6.3 times 10 to the ninth power. Okay, so what it lets me do is it lets me handle the powers of 10 separately from these guys. So now here you can see that I've got 1.1 and 5.5. Now that can simplify. So I can have 1.1 divided by 5.5 times 10 to the negative third divided by 10 to the negative eighth. And I'm going to do these separately. This becomes 1/5. And this becomes, right, 10 to the negative third. So it'd be 10 to the negative 3 minus negative 8. So this is 1/5 times 10 to the 5th. Now, I happen to know that 1/5 is 0.2 times 10 to the 5th power, and here's a problem. This is not proper scientific notation. I need one integer to the left of the decimal. So I'm going to move this item, right, this decimal place to the right. That means I'll take one power of 10 away. So it becomes 2 times 10 to the 4th. All right, to practice scientific notation, please pause the video and do these 3 problems. And now we'll proceed and we'll solve the problem we originally started with. Now, I have to know some things. I have to know the volume of a sphere is 4/3 times pi r cubed. So I need to know this formula. And if we take a look at this information, I have r is the sun's radius. Betelgeuse is 1,500 times the radius of the sun, so 1,500 r becomes Betelgeuse's radius. And if I want to have a ratio, I'm going to put Betelgeuse's radius, or sorry, Betelgeuse's volume, 4/3 pi times 1,500 pi cubed over the sun's volume, r cubed. Right? I'm going to use a property of exponents to separate these, right? These are products being taken to a power, so I can do 4/3 pi, 1,500 cubed r cubed, over 4/3 pi r cubed. And now I can start canceling common factors. I have 4/3 and 4/3. I have pi and I have pi. And I have r cubed and r cubed. And I just end up with 1,500 cubed, which is a pretty big number. Right? So that becomes 3,375,000 times the volume of Earth. Right? How many times is great? 3,375,000 times as large. So that's a very, very, very large star.